for me, it's a pleasure to introduce Carmen. So for the history, with Carmen, when I arrived basically in Saclay, I found Carmen in my office. So it's a long story of friendship more than anything else, but also working together for many years. And if we are here today, it's also thanks to Carmen, because a few years ago, Carmen organized in Baeza, in Andalusia, very nice place, surrounded by olive oils. So you should visit if you haven't been there. Perhaps we can organize another one. Sure. Yes, Carmen organized a workshop on Mediterranean cyclones, where I met most of you. And yeah, so then this is a sort of follow-up from the discussions that we had there. And yeah, and in that occasion, I also met Susanna, so it was really nice. So today, Carmen is back to Spain and still affiliated with Bologna, with the CMCC. And she's going to talk about predictability of the low pressure system leading concurrent events in the Iberian Peninsula. So thanks, Carmen.
Okay. Thank you very much, and all of you. And what for me is, I'm sorry because I will talk about the Mediterranean cyclones properly. So I'm a bit, foreign now, because I will talk about the low pressure system, intense low pressure system in the Iberian Peninsula. And yeah, as David said, I'm still affiliated to the CMCC, but I'm working mainly in the University Pablo Olavide in Seville. And this is a collaborative work between the people in Seville and also with the oops, sorry. So yeah, well, the concurrent extreme events are simultaneous occurrence of extreme values for multiple variables, and this is something that it's happening sometimes with this kind of low pressure system. So this is the main reason actually to try to investigate or to understand how is the behavior of this kind of low pressure systems. And for instance, the storms like Filomena in January 2021 cause concurrent events in the Iberian Peninsula, well, wind gusts and maximum of accumulate precipitation in a very short time. And mainly the snow in places where it was not really common to have this kind of snowstorm. This is an example of this case of the Filomena for the case of snow. Particular Madrid was recording one of the heaviest snowfall in over the century. And well, the purpose actually is a collaborative work, as I say, between two European projects. One is CLIN and the other is AIDA, where David is working. And both are sisters or brothers in the European Commission, because we are working with the same topics, no? Detection and attribution of extreme events, and using artificial intelligence. And the idea of this work is an ongoing work, I have to say, which is not still finished. We are working on this, and is to investigate whether a specific atmospheric circulation leads some events, and will have been possible in the absence of the climate change. So the idea. Okay. Oh, no. And a study of attribution and to investigate the predictability of this kind of events. And first part of the presentation, I will show an overview of this kind of low pressure system affecting the Iberian Peninsula, and then the assess of the predictability, understanding the predictability, like working with the dynamical system theory, with the I don't know if you are all familiar with the. Most of you, yes. I don't know if all of you are familiar with the work of Davide. I think so, but okay. In any case, I will introduce some part, and then we perform an attribution study of all of these systems. This is also in line with the discussion of yesterday when we were discussing about the definition of the Mediterranean cyclone. Well, in this case, it's the definition of how to name the low pressure system in this case. In Germany, they have named the intense low pressure system from 1954. And not only the most intense, also some other low pressure. For instance, Klaus in 2009 or Cynthia in 2010. And but just from 2017, the Meteorological Service of Spain, Portugal, France, Belgium, and Luxembourg start to name the storms just to put aware to the population in the countries. Because when you have some names for the hurricanes, hurricanes, or for whatever, the people seems that they have they put more attention into the possible impacts. So the way to define from this meteorological service, the way to define this intense low pressure system are they have to be a storm or depression, so a type of cyclone. Still in these countries, when we hear in population, they are understanding like typhoons or hurricanes, hurricanes. But a cyclone is also a low pressure system which is affecting these places. So, well, the low pressure system where the winds rotate counterwise in the northern hemisphere, that has associated strong or very strong winds, which will be more intense the lower the minimum pressure in the center of the low, of course. And the storms that will be named will be those that deepen in such a way that they can produce a great impact on the population. So the other kind of low pressure systems are not having a name here. And they are not necessary to experience a process of explosive cyclogenesis. So it's just that may cause some impacts in population. Why? Just because to be aware, for the population, because we have many impacts. So yes, precipitation, accumulated precipitation in a very short period, or wind, some problems with the sea, with coastal areas, and snow, or also some winds. All of these are pictures from the last year, actually, during the impacts of the low pressure system there. This is the names that they prepare every season at mainly in September, more or less, when the seasons for the low pressure are starting. They have a collection of names, and they are started to name this low pressure system every time that is the country which is affected first, the one to attribute the first low system. No? And we have created a collection. We have prepared a database. This is part of this database. With the collection of all there are many of them. This is just a piece of this database with the intense low pressure system, the meteorological service, which is this low pressure system, the season, the duration, the damage, how many people is, or another observations that we have there. And mainly the things that we have in this collection of this low pressure system are, well, the name, the date, the year, the duration, the accumulated precipitation, the maximum precipitation, the location of where was that maximum of precipitation, the same with the snow, same with the wind, and other meteorological events associated. For instance, if they have some impacts in the coastal areas, and or any other impacts. So many alerts from different service and some observations or some endurance disease or whatever they have. So this is how it looks, the frequency of the occurrence of these low pressure systems. And this is in the y-axis. We have the duration of the in days. All of these are from 2017, which were the names of the low pressure system, to the current days. And well, we can see that there are few of them that are lasting a lot for a low pressure system with this intensity. And yes. The duration is every time that we still have some impacts in the population, some intense precipitation or winds or snow or something related like this. No, not at all. In terms of the precipitation, snow or wind, all of them. Because it's when the population is affected. It's mainly when the most part of the population is affected to this. Well, it depends of the minimum of the precipitation of the so well, this is the threshold, let's say. So, for instance, when we are talking about winds and damage, so those are one of the location. In red is when we have some problems with populations and disease or some impacted in the population, and those are the locations where they mostly affect in the Iberian Peninsula, and yes. We are not, well, we are in the Iberian Peninsula. Well, Spain. Yeah, it's the Iberian Peninsula, but you are right. Focus in the Spain. That's true. Yes.
I mean, this is like also when we do the study in France.
Yeah, I know,
France,
but
then we have
yeah,
these,
well,
geographical borders, and you don't know what's going on the other side.
yeah, no, but actually, it's yeah, well, it's basically it's in a space focused. I'm sorry, but it's focused in Spain when it's affecting really in impacts in the Spain. So also there is well, this is a kind of yeah, saying of kind of analysis of total duration in this in terms of days, and in situations where we have sun snows in the with yeah, over a certain threshold in this way as well, and those low pressure systems were the most intense in terms of this kind of maximum of winds, precipitations, and snow, and also affecting to with some serious problem in the population. So when we have well, when we have some deaths as well, and so many problems, damage in general, and so this is that was all about the kind of low pressure system that we are applying this kind of study. Then the access to the predictability, we are talking about the predictability like an intrinsic predictability of certain extreme events, and this is related to the work of Davide. And so using two proxies like the persistence and the local dimension, we are able to assess how is it is already demonstrated that in several articles, and several people here in the room has used already, have been shown to be good proxies for in order to study the intrinsic predictability of a certain event. The idea is that we have the persistent and the local dimension. So, for instance, if we have some atmospheric circulation in a certain day like this, so when we have the local dimension here, we have two, like the local dimension will be equal to 2, because we have two possibilities to go after this, and also we have two possibilities to arrive into this kind of situation. And for the persistent, theta is the inverse of the persistence. So if we are staying in this pattern, so we are having 3 times this pattern. So the theta will be 1 divided by 3, because it's 3 times in the same kind of pattern. Otherwise, when we have this kind of situation, we are changing the pattern every time. So theta will be equal to 1. And at the end, following the study of Davide, when they focus also how was looking the limit underlying attractor using these properties, they realized that in the streams of the underlying attractor, they found the most predictable systems where this one where the local dimension is lower and the inverse of the persistent is lower, and they were related to this situation of the NAO. And then when we are higher, higher theta and higher local dimension, the systems are less predictable and mostly related to Atlantic region or blocking. So following this idea, we have selected the peak of this kind of events. So in terms of all of these ingredients that I showed before, and those were the most impacted low pressure system. And what we can see is that, for instance, Filomena and Gloria are streams in this kind of that means that talking about the dynamics behind of this low pressure system, both were a bit those were a bit rare, like in terms of atmospheric circulation. So the idea was to go a bit farther of this, and also following the recent study that were in the room contribute as well, mainly for the case of Filomena, but we are not just focusing, even if I will show you a bit. So this is the sea level pattern of the sea level pressure pattern of Filomena, and the composition during the whole event, and in the characterization, let's say, for the precipitation, snow, winds, and temperature, and also in some altitude, so in the geopotential height in 500 hectopascals, and in 300 hectopascal as well, the U and the temperature. And what we can see also is that that we found some weird patterns in the SLP, which are actually the ones that cause these streams in the attractor that I showed before, in the streams in the local dimension and in theta. And performing this attribution study following this study of 2022, we divide first of all in two periods. So following the same kind of way, the factual and counterfactual, in two periods. So 1992 to 2021, and from 1950 to 1979. So in blue. So here we first show the quality of the analogs. So we search for analogs regarding this low pressure system in the peak there, and so we compute the analogs for that day, and we can see the quality of the analogs, the local dimension here, and the persistent here. And in the quality of the analog, what we can see is that we are a bit far of what we found in the analogs when we are looking to this kind of pattern that is affecting, and the pattern that it is related to the most part of the impacts there. And in terms of predictability, looking at the local dimension, we see that there are some difference between the two periods. In the most recent period, we have a shorter local dimension, since in the first part of the period we have a kind of difference. We are losing this kind of predictable. We are having more predictability in the recent period, let's say, in terms of local dimension. In terms of persistent, we have higher values still in the first part of the recent part of the period. And when we are looking to the AMO or the ENSO, there are not really special changes there. The same that for Filomena, we did for the other low pressure system, for instance, Gloria, that one of the most important as well in Spain, sorry, the Iberian Peninsula. And this is the characterization also for the precipitation, snow, wind, temperature, and the sea level pressure. Well, and all the characteristics, and actually it was the low pressure system, which is not that evident, but coming also from the south, which was something also in common with Filomena. And And when we are looking to the analogs, we see exactly that very similar to the same that we found in Filomena. That the analogs are very far to the low pressure system that lead kind of very impact events in Spain. And in terms of predictability, it is something very less predictable, let's say, because the local dimension is very high. And there are also some changes between the periods. In terms of persistence, there are also some changes between the recent period and the first part of the period. And still no significant changes regarding ENSO or AMO. And when we compare with all this kind of low pressure system in terms of analogs, we find some common things that most of these low pressure systems are very far to the specifically for the pattern that we are interested with, because it's the day where we have the peak of impacts, not in terms of the damage, just in terms of maximums of precipitation, wind, snow, all of these events at the same time. And usually we have a very rare pattern, which is not, we cannot able to find in the analogs. And in terms of predictability, well, there are some differences between some of these low pressure systems, but indeed, well, there are, for instance, in Lola, there are also some changes in the recent part and the first part of the period, but we cannot say, okay, we are going until more predictable low pressure system, because all of them are a bit different in this case in terms of predictability. And we are still in this line. As I said, this is not still finished. We are performing this attribution study in different situations like this. Actually, we have to also go farther back in time in order to put the same requirements that they used to name this low pressure system in the present days, but in order to investigate what happens in the past as well, and taking advantage of the analogs as well. So in summary, just it is essential to study this intrinsic predictability to see and also to study the potential of the analogs in order to attribute this kind of low pressure system to the climate change, or to see how rare is this kind of events. And in the case of Gloria and Filomena, even that the meteorological service was able, well, all of them were able to predict, to forecast this kind of events in that intensity, like those at the end were in Spain at least. So this is the way also the motivation also to try to understand what might be the driver to associated to this kind of low pressure system that are very weird in the historic data, that in the reanalysis and all of this. And it will be also essential to study this in different models in order to see how are the projections related to this kind of patterns. And this is all from my side.
Thank you, Carmen. So now we open the seminar for questions. So yeah, thank you for this talk. In the task of naming storms, do you think that the presence of some regional centers in some countries like Spain, in the case of Galicia, Basque Country, Catalonia, maybe other like Italy, is a problem, or they agree with the official and national level institutions when naming these storms? Because, of course, I agree it's very useful to communicate to the public, but I don't know if you are aware of any problem in this sense, or there is a good agreement.
Well, up to my knowledge, I know that they are both in the agreement. So all of them, all the meteorological service are in a consensus for how to name, or how to say, okay, we are now officially is starting this
name, and we follow the
exactly.
track of this.
And they start to put some alerts to the population in terms of winds or in terms of to the question to if it's subjective or not. Actually, no, because they are starting the alert. So the duration is all the time that you have a risk of because you have a certain level of you are over a certain threshold in terms of winds or in terms of something over the normal, let's say.
Yeah.
And yeah, since they are all in the consensus to how to name the low pressure system, they are. I assume that they are using the same.
But I'm not sure. Sometimes, you know, there are these regional problems, and so maybe, I don't know, Catalonia may decide that when the storms comes over the territory, it has another name, and then recovers it.
No, usually they are keeping the name. Even if it's just affecting France or if it's just affecting Spain, they are just keeping the name.
Thank you very much.
You know, yes, Susanna.
So I'm curious, because when you listed the countries, you did not list Portugal, right?
No.
So they are not part of them. I'm just curious. They're not.
No.
Part
they
of
are.
this?
Yeah. No, they are.
Oh, they are. Okay.
They are in the list of. Yeah, they are.
So it's just.
I'm not using the low pressure system when they are just affecting Portugal. I'm just using when they are affecting Spain.
So, but they are.
But they are in the same system. Yes, they are in the consortium.
Okay. Just trying to understand.
And sometimes they receive, well, they have some low pressures that are not affecting Spain. It might be possible, yes.
Yeah. So yes.
Just more out of curiosity, maybe you know the answer because I don't, but what do simple models of like moist QG turbulence tell us about how predictability or the persistence of these events, how it might change with warming?
I think this is something very interesting to apply also here. Yes.
And then
Definitely.
and Erika Madonna about this, where we do the predictability and the persistence in the quasi-geostrophic model. So basically,
and not only also what happening in the stratosphere and related to this, and as I said, well, this is something ongoing, and but the main purpose is this one. Yeah.
We can give you some reference for this. Yeah, I had a comment myself that basically in what we do also with these dynamical indicators, we see that there is in winter, there is a lot of zonalization of the flow. This is the PNAS paper 2023 that we did with some colleagues. But so these storms, they are so rare, and they still happen, and there is no trend in frequency.
No.
And I think the hazards are also enhanced by the fact that there is a lot of convection around this storm, even though they are still kind of baroclinically driven. So they are kind of strange animals, and we see some of them also. Well, in Italy, we have more of Genoa law, we have more of these storms. But in Spain, they are really strange animals.
Yes.
And now they produce a lot of rain, a lot of hazards when they happen, because the temperatures are much warmer in this area. And so they have a lot of convections embedded. And in winter, they can produce a lot of snow. So I think it's definitely like a topic that is very interesting to study for this area, the Iberian Peninsula, because it's basically where you reach all the there is
all the Atlantic low pressure system coming directly from
and also for south of France, the area of Pyrenees Oriental, it's very important.
Thank you. No, I wanted, like, your comment made me think, like, are most of the systems that actually impact Spain, the ones you chose, are they from the Atlantic, or are some of them from
depends.
The
There are mix of them are coming from the, well, usually in Spain we used to get the low pressure system coming from the north, from the Atlantic, but not always. And for instance, Filomena and Gloria, they were coming from the south. And with the composition of weird composition of the low pressure system and some blocking of the anticyclone, so those are the rarity, let's say, of this kind of low pressure system, and this is what is more mostly affecting in terms of impacts of of the concurrent events at the end.
Okay, so the ones that come from the south are worse than the others
in this case, when we are listing all these great impacts, yes, they are more.
Same also for Italy sometimes when you have this ridge that forms.
Also because of the warm,
yeah.
Also because of the warm.
Last question.
I just wanted to emphasize this this idea. The two most catastrophic extratropical storms in the Balearics have an African origin, in some sense. Well, of course, the trough comes from the north, whatever, but there is a genesis of very strong baroclinic zone in North Africa in a poorly observed lands, let's say, and this evolves then northward towards a very huge and intense extratropical storms.
Usually it happens like this because
so that's very important. It's a problem because the area is not so well observed as many other.
And when you see that in the analogs, for instance, you cannot find anything similar in the. So that's why the idea to extend to further in the past and also using some models in order to see how are this pattern evolving in the future.
Yeah, no, it's the same, and these storms are also very hazardous for south of France because they trigger the precipitation Sevenol in the south, in the area of Montpellier. And for north of Italy, we have many cases where we have this genesis of these storms over Africa, and then they're blocked because they cannot go to the east. They are stuck on the Mediterranean, and then it's hundreds of millimeters of rain over the Po Valley, and we have the historical floods in. Yeah. Yeah, so lots of strange beasts around. Thanks, Carmen, for bringing them up. And yeah, let's thank Carmen again. And now we have Pier-Luigi. Some reminder while Pier-Luigi, we have on the blackboard the list for the Canard night tomorrow night. So if you want to go to Paris, well, there will be not only Canard, you can eat other things typical from the Southwest cuisine, including vegetarian options, piperade, for example. So you can subscribe on the blackboard, and whole time is going to be 6 p.m. tonight, and then I will make a booking in some restaurants. I will tell you. And yes, there might be Canard also. And on the blackboard it's for tomorrow. And when do you want everybody to next time? Do you have a deadline? For tonight, for tomorrow night, the deadline is tonight 6 p.m. because Friday night in Paris is busy, and otherwise we won't find the table. Okay, then yes, I think that's all for the moment as announcement. So the next speaker is Pier-Luigi Vidale from the University of Reading and the National Center for Atmospheric Science. And Pier-Luigi is gonna bring us beyond tropical cyclones.
Well, in terms of what I've been doing.
Thanks, Pier-Luigi.
So unfortunately, I cannot be here in the last 2 weeks, but we've been moving steadily into finer and finer scale. So I'll start with tropical cyclones and take you a little bit towards the things we've been doing. You'll hear more from Malcolm if you stay for the last 2 weeks about tropical cyclones. Yes, of course it's not working.
It's working.
Is it? Okay, it's a bit of a lag.
If there is some delay.
Okay, just say about our philosophy. So we are global modelers. We are interested in the global climate system. So in many ways, if you look at what I said here about our focus, we are interested in upscaling. We are interested in what small mesoscale things do to the rest of the climate system. So it's sort of a different way to look at it. So we're interested in interaction. In terms of tropical cyclones, I still remember many, many years ago, I was at a meeting at the National Science Academy, and Henderson Sellers came up with this funny sentence, what is wrong with nature? Because at the time, global climate modelers were confronted because they consistently produced tropical cyclones in the Southern Hemisphere, and people kept saying that there were no hurricanes in the Southern Hemisphere. And then we did have something. We can still debate what it was, but we did have something. And in many ways, this made me think because at the time I was very much involved with mesoscale phenomena, and they were very poorly observed, and it was very difficult to come up with what was realistic, that often models could be seen as physical labs, and part of the reason we bother to have models is to interpret, challenge, and complement. So in this case, I'll show you some example of catalogs of things that we can form with models, and also to test hypotheses, not just about reproducing what has already been observed. It's important to use them as labs. I will skip the history of the lab. Yep. Yeah, maybe you're right. I would skip where all of this came from in terms of PCs, which started for us with work in Japan, and then we were part of the US Hurricane Working Group. And I will mostly focus on these scales, 25 and 10 kilometers, and I'll say a few things about the 2 kilometers. I put in this table what is our capability, so what the duration of the experiments is, and what the typical sample size is, whether or not they're coupled, so that you have a summary. Just remember, I'm talking about global models, so they are quite limited in terms of ensemble size and in terms of duration. Okay. Back then, when we had this activity, the Hurricane Working Group, things were quite simple. As we increased the model resolution from about 100 kilometers to about 20 kilometers in most of the models, we went from having very few tropical cyclones or no tropical cyclone at all to having a reasonable number. So this is the frequency per year in the observations, and this was our resolution chain, and it was quite typical in most models. And what emerged at that time, in fact, was these hurricane-like or tropical cyclone-like vortices responded well in terms of interannual variability. So although we didn't have the full range of intensities and all that, they were located in the right places, and also they responded to the environment in a credible way. So that was sort of the state of the art. What we decided to do for many reasons at the time, so post-Hurricane Working Group, was to set up high-res MIP and this project Primavera in Europe, gather several groups, and we all did experiments together. So we had both atmosphere only and coupled experiments, and we had a control experiment with no greenhouse gases beyond what was there in 1950, and then we had a historic experiment going to 2050. And so we looked at whether this result was robust in a much more coordinated experiment. This clicker is really not collaborating with me. So this was one of our results from Malcolm Roberts' paper at the time. This is the tropical cyclone track density in a number of Primavera models at 100 kilometers. This is what observations tell us what that distribution should be like. And if we increase the resolution, you can see what happens. We have a more realistic track density, but we also do have quite a model diversity. And at the same time, in the same paper, Malcolm looked at the structures. So we have on this side, the really weak storms, and on this side, we have what should be a category 5. These are all the models. And again, if you cycle through those, you can see that as we increase the resolution to 20, 30 kilometers, we start to have more and more of the category 5s and structures that start to look like tropical cyclones. Again, we're stopping at 20 kilometers. We're still very far away from what people would consider with regional models to be the adequate resolution for this. The other thing that Malcolm looked at the time was the wind pressure relationship. So this is again ID tracked. These are the observations. And these are all the models from 100 all the way to about 20 kilometers. And we have the low and high resolution equivalents, and we also have in the mix some models that are coupled and some models that are in atmosphere-only mode. But just to say, as we increase the resolution, these relationships, in the same way as we saw the structure more realistic, this relationship starts to tend toward what the observations say. Perhaps at the time with this French model, this is the CNRM model, it was questionable. They should have such a good relationship at 20 kilometers. There are theoretical reasons why we wouldn't expect to get such a good relationship at 20 kilometers. We think that is something that we should be able to reproduce at 10 kilometers or under 10 kilometers. The problem here was also that different groups defined resolution in quite different ways. So there was one group that, because traditionally they run at 300 kilometers, defined their high resolution to be 80 kilometers. And in our case, we define high resolution to be really 20 kilometers. So although we had coordinated this, it was not a strict enough protocol, and people were taking a bit too many liberties. But I would say some of the main results were from the hurricane working group and things we were doing before were confirmed by this very coordinated experiment. So that was Primavera. We have a new project called Erie, and in Erie we are just about the same people, maybe fewer models, but we are trying to research. We're trying to put together HiResMate version 2. So we're a bit more ambitious. We aim for longer simulations, or 150 to 250. And the focus resolution is 10 kilometers. In particular, the focus of this is the ocean. So what is new in Erie is that we are going to have eddies in the ocean that are nearly entirely resolved. And we want to understand how these eddies perform the mixing and how they form things like boundary currents and are responsible for meridional transports, and whether or not all of this then affects the large-scale circulation, affects teleconnections, and again affects the rest of the climate system. And we already know from some NCAR experiments that if we have an eddy-rich ocean, the internal variability system is going to be larger than if we use a parameterized ocean. So we have a more lively climate system, and we might have, as a result, more lively teleconnections and more lively weather regimes and all that as a result. But just to say, we are focusing on 10 kilometers in the atmosphere, 10 kilometers in the ocean. So there's plenty of opportunity here for looking at all sorts of storms. And so in preparation for that, what I did was to run a number of atmosphere-only experiments. So in this plot, I now show you the results from just the atmosphere-only experiments with hydrogen-free at 60 kilometers, 25 kilometers, and 10 kilometers. And you might notice here something already a little bit strange. I told you before that as we increase the resolution, we normally have more and more tropical cyclones. But in fact, if you look at the track density, in this particular model, at 60 kilometers, we have more. And the reason for this is that some of the groups in the development of models for Primavera and still in development of models for Erie are using stochastic physics. And I have a whole paper that is listed somewhere here, yes, that discusses the equivalence between and the use of resolution for hurricanes. But just to say that in the past, we used to converge from a low number to just about the right number. And now we start from having way too many when we use stochastic physics to having, again, just about the right number for a number of reasons. And I call it a natural selection paper. But again, as we go towards 10 kilometers, we start to have the right distribution. So this is the difference between two of the ensemble members and one of the ensemble members and the two force of resolution. So we reduce the number, and where we reduce the number is category 1. So it's very weak for them, and we go to 10 kilometers. The other thing that happens at 10 kilometers is really interesting. I think this is quite a big deal. Is that if you look at this is pressure versus latitude. So if you look at the latitude of maximum intensity, at 100 kilometers and 60 kilometers, but even at 25 kilometers, you have weak storms that also tend to develop at quite high latitudes. They don't really develop in the tropics. And as we go to 10 kilometers, you see that first of all, we have many, so this is the really low pressures here. We have many more in these low pressure categories, but you can also see they don't go as far north. So they tend to live more in the tropics. In that sense, they're much more tropical cyclones than they are 100 kilometers and 60 or even at 25. So this is the difference plot. So this is the three ensemble members subtracted from the lowest resolution. So this is quite a systematic behavior, and I think it is important that we have this result. In terms of the pressure-wind relationship, so this is just for our model now, and this is atmosphere only, so it's a bit exaggerating, of course. But this is, again, the IB tracks. These are three of the basins that we look at. And this is the lowest resolutions, and in red, in red here, over the three basins, the 10 kilometers. You can see it's pretty good now. It's quite close to observation. And in so many ways, I remember Carrie asking me if I was expecting anything very different, 10 kilometers and 20. And I said, nah, it is actually quite a big jump compared to the jumps we had before. And maybe the fact that we are now living in the tropics, these things are spending more and more time in the tropics instead of going out to the extratropics and re-intensifying for other reasons. Maybe that's part of the story. Just to say that also in terms of intensification rates, the 10 kilometer is able, this is just for pressure. So this is the same three basins. And this is what's happening a few hours before and a few hours after the maximum intensity. And again, the 10 kilometer model comes very close to observation in terms of pressure. The wind is not as good as what we see here. So at the same time, Stella mentioned it this week, we came up with this project that is funded by both UKRI in the UK and NSF in US. And one of the questions that came up this week from someone was, oh, have there been or do we expect hurricanes hitting Europe? Well, there have been all sorts of things hitting the US side with all sorts of natures, and there have been many close calls. And so one of the questions that we have is what exactly is making landfall? Are these actual hurricanes? Are these post-hurricanes? We came up with this name, cyclones of tropical origin, to cover both the canonical tropical cyclones and things that are remnants. They have some remnants of warm core, but they might not be as symmetric as the proper tropical cyclones. There have been quite a few cases, and we now have an opportunity to augment the sample size using a number of operational products, and also at the other extreme, these climate models we were just talking about. But part of the story is can we distinguish all these different types of storms? Can we try and come up with the same type of realism that we have in the very high resolution weather forecast, for instance? Just to say that one of the drivers for this project is the fact, and why should we care what makes landfall? So this is from a paper that Alex Baker published a few years back in JGR. So he was looking at storms that make landfall in North America and things that make landfall in Western Europe, and classifying them using a number of reanalyses into warm core, all sorts of hybrids, and then what we would consider to be extratropical cyclones. And if you look at the history of the wind speed just prior to landfall, these different storms have quite a different history of this wind speed. So from the point of view of the impacts, both on the US side and on the European side, does matter. So in terms of the timing of the maximum, but also, of course, then in terms of the distribution of the wind, the nature of the storm that makes landfall matters. So it is important we know what arrives, that when we find them, we can tell what the structure is and what the history is. So as I said, we're using a number of sources. So we're looking at things that are very abundant, but low resolution, perhaps not terribly suitable to look at something that requires a very high level of physical realism. But maybe we can look at variability, and we look at the environment. At the other end, we have very high resolution regional models, convection permitting regional models that can be studied. In the middle, we have these models I was telling you about in this sort of 10 to 20 kilometer range. And some of them are climate models, some of them are seasonal prediction models. We have also a number of reforecasts from different operational centers. And also we have the models trying to go to kilometer scale that will increasingly give us realism. So the idea in our project in Huracan is to use all of these together because they provide a huge sample size and each one of them has strength. So one of the things I did with the climate model, I asked the question, okay, can we separate what is warm core symmetric storm, so a proper tropical cyclone, from what is everything else? And I took, so here is the Ivy tracks. I took everything that is in Ivy tracks that I normally use to define what should be. And then I took from Ivy tracks the things that are defined as having a proper warm core, and then the things that are considered to be of the ET and SS class. And then I use the hard free space analysis in our model to again start from the storm track and then to separate what is really a warm core and symmetric storm and what is everything else. And so in many ways, so going back to what Henderson-Sellers was saying, if we look at the observations and we look at South America, so we had that storm Catarina, which was considered to be a hybrid. But also, if you look here in this region, you can see that both on the Atlantic side and on the Northwest Pacific side, we have a number of storms that sit over the Kuroshio and sit over the Gulf Stream that very likely are hybrid storms. And we start to have quite an agreement in the places where we could say there are good observations. And then in places like this, where nobody's really paying much attention, it's possible that close to Australia, we do have a good observational foundation, but here, nobody's really looking because these are particular classes that are weaker and the operational centers don't really have a definition for. While here, when we're talking about the category 1 to category 5 storms particularly, the operational centers have a good definition. And if we seek homogeneity across the planet, there will be a much better agreement between what the models are simulating and what the agencies are telling us. We had the same exact controversy with the reviewers when we submitted the paper with Kevin Hodges looking at the reanalysis. There was a lot of pushback about things that we found down here because basically these weaker storms are not in the catalog. And Kevin had to show them storm by storm what is in the individual operational centers catalog and what is not in IB track and all that. Just to say that having a climate model that can do this is one of the ingredients of the study that we want to perform over this region, where we want to separate what is a canonical tropical cyclone from what is a remnant or a hybrid storm. Oh. So this is another part of the study. This is from Leo Safin. What he's doing is he's looking at hindcast. So he's taking everything that the hindcast can produce, and he's looking at where they originate. So with the idea that they make in our region, he's looking at all the origins over the Gulf, origins over Africa, or non-traditional origins, so things that might develop much later. If you look at these colors, they tell you this is much later in the season. Things that might develop at high latitude and still impact Europe. So this is just one of the set of ones we've looked at. We have thousands and thousands of such storms, and we can find them, we can catalog them, we can look at their structure, and we can decide how many of these represent a variant of things that we have seen in the observations and help us augment these observations. So he's been doing this quite systematically through all the hindcast. I'm saying this because this could be a source of information for storms that occur in the Mediterranean. So we were coming up with these names. It's just because I keep talking to journalists, and I had an interview last week, and I was talking about cyclones, and the journalist understood cycles. I thought I would put up this cartoon. But there is also something that just came up in the literature, this thing called Cyclops, which is one of these frameworks to find all sorts of storms and categorize them. It has an incredibly sophisticated chart. It tells you all the ramifications of the discovery and classification. So that could be an interesting source of capability for the community. So because of the talks I saw earlier this week, I went back into my storm catalog. This is again from the climate model. I went to the stage where we just identify a warm core, but we have not yet used the phase-space analysis. And I just focused on this region. And so I extracted from the ensemble, I extracted some cases in which I see things that had a warm core. So these are what we categorize to be tropical cyclones, and the color, where they're black, they don't yet have a warm core, or at the end, they have lost their warm core. Where they're colored, they have a warm core, and this chart tells you what the pressure is. So this is all the storms that did have a warm core, and I saw entering the Mediterranean that I found in the climate model. And there are some really interesting examples. We were talking about these gaps in the orography and things that travel through. So I found quite a few. These are my 4 favorite ones that I found on Monday after we talked. And then I found some others.
And these are in current climate.
Yes, this is historic. Yes, this is with historic SSTs. these are runs like I ran from 1980 to 2014. That was part of how I was made, yes? So this is the first set that I found. And then I found a few that enter the Mediterranean and retain a warm core. So with funny, interesting, funny cracks. So I found 3 that had quite a nice elongated. So again, there is some warm core. If you were to pass them through phase-space analysis, they would probably drop out as not having the proper symmetry and all that. But again, these are now the things that we could attempt to analyze with a specific definition of what we mean by an X-cyclone or a medicane. Yes. I just cut the and then I looked by eye. What? Yeah. I did this on Monday afternoon really quickly. I did not try to. So this was after the talks. I just became curious and I went back and I ran very quickly all my plotting and I plotted all the ensemble members I have and I just selected by eye. This is the old style machine learning. You just stare at things and you pull out. Yeah. And then I found a couple of examples of things that originate, in this case over North Africa, and or coming from the Atlantic and go through North Africa, and then generate a warm core over the Mediterranean. So these are 2 examples of things that only developed a warm core over the Mediterranean. They did not have a warm core before. So this was a quick scan of my existing tracks, and this could be done a lot more systematically and a lot more objectively once we agree on things that we could be doing. How am I doing with time?
5 minutes.
Okay, so I'll just say a few other things. So just to say, I wanted to point out that I find this to be really quite fascinating. That at 10 kilometers, these things spend a lot more time in the tropics. Alex Baker will be here in the last 2 weeks. He's looked at the next generation model. So this is the sub 10 kilometers models in next gens, all the way to 2 kilometers. And he's looked at pairs of simulations in both the IFS and ICON, and he's found the same relationship. As we go towards 3 kilometers, many of these models start to produce deeper storms and also start to spend more time in the tropics. But there is, of course, a lot to be said about model formulation. It's not just about resolution. There are differences in what is done with the convective parameterization. So just to say, there are a number of products out there. So there is the Destiny program in the EU. There's this project I was talking about, NextGems. There is a German project called Warm World, and people are running these models in this space, 10 to 2 kilometers, for a few decades each, and small ensembles, very small ensembles, but they are interesting. And mostly what they're doing is they're dropping convective parameterization in the atmosphere. So I had this result from our model with convective parameterization, and this is a plot from Alex about models in the space between 10 and 2 kilometers. And we are coming again close to ID tracks in terms of the wind pressure relationship. But you can see there is quite a range of things. And this has to do with decisions, what to do with turbulence, what to do, whether the full set of convective parameterization has been disabled or whether just the deep convective parameterization has been disabled. So if you want the details, ask Alex when he's here, and or read his paper, which is under review. Well, it was basically accepted with minor revisions in GRL. So it's not just the resolution. There are many other things that still do matter. The other thing that is in Alex's paper is the rapid intensification. So this is quite interesting. So he's looking at these 24-hour intensification rates, and some of the models, and this is the best one, I would say, at 4 kilometers, has something that really starts to resemble observation. So this is sort of the next. So we did the intensities quite well, and as we go towards kilometer scale, it looks like for some of these model configurations, we can also get the rapid intensification. So this is really quite interesting that we have that result at those fine resolution. So that one is at 4. That one is ICON, the latest incarnation of ICON at 4 kilometers. Yeah. We had something like that on one of the IFS at 2. But again, people keep, this is a project in which we are developing models. So people keep changing Smagorinsky, changing the amount of mass flux and this and that. So this is the plot that has the most years just before they went to production. So now we'll have the long production. This might change when we have tens and tens of years of this, but this is the end of the production, of the model development phase. Yeah. A few years ago, we had a project called Diamond, and Falco Youth wrote a paper about, again, intensities and all that at around 3 kilometers with 40-day simulations. We're now proposing to go to a whole year with a number of groups worldwide. So not just Europeans, but including everybody around the world. Excellent, yeah. Yeah, he will probably show the results from this. Yeah? At the time, we were quite interested in understanding. So in my paper with stochastic parameterization, I was looking at the seeds and seeding rates and all that. And one of the things we were looking at also was organized convection. So we plotted for our diamond simulations, we plotted what happens at 100 kilometers with organized convection. This is things that come out of the Sahel, and some of these could be seeds for tropical cyclones. And then we looked at the same exact organized convection of 20 kilometers, and then 10 kilometers still with convective parameterization, and then disabling the deep convective parameterization and disabling everything all the way to 5 kilometers where everything is off. And these are the observations. And you can see that if you look at convection, there is still a strong contamination by the diurnal cycle. We do have these episodes of organized convection, and we have found that some of these indeed become hurricanes. But the simulation is very strongly contaminated by the factor. You could also argue that maybe the thin speeds are not quite right in some cases. But we've been building on this for a long time. So we are currently running a long climate simulation like this. And we are going to run 30 years of this one to try and understand what happens with these different decisions. Well, at the 10-kilometer range, we're trying to understand, it's strange in so many ways, it's stupid resolution to work at, but it's what we can afford at the time. To understand what happens when we disable all these things. In the future, we will have scale-aware parameterization. So the formal, maybe Malcolm will talk about it, is following Arakawa Sensei's ideas will allow us not to have these on-off kind of decisions. But following all these things is one of the objectives of the work we're doing now, and also understanding what happens with these errors in the diurnal cycle and what happens with MJO and all that. So we found some of these to generate hurricanes. We also found that there are some strange behavior over land in one of the simulations. We've then gone out to look at other models like ICON and IFS. We looked at the same things. And we've also tried to connect what's going on in these models with what's going on with circulation. So there's here a period in which all of these systems travel, but when they get to the ocean, then they die off. And then suddenly somebody opened the door and all of them started traveling. They're very, very organized. And we were looking at what was happening with the circulation of it. So we want to look at several seasons. We want to look at several large-scale configurations to understand which ones of these may end up being a seed for tropical cyclone. And again, there are lots and lots of decisions in these models about what to do with the convective parameterization. Shambo Feng, who might also arrive in the end. Yeah, he's been looking at easterly waves. He might talk about that. And again, we're looking at anything that could become seed for tropical cyclones. So there's a wealth of data that we've been analyzing. Just to say that in between, I've been teaching myself how to use one of these MCS trackers. So instead of just doing Hoffmüllers or Precip and all that, we have started to track each MCS individually. This is really heavy. It takes much more to do this than it takes to do the simulation, but we can then attribute precipitation and winds and all that to each object and study the size of the object, study how fast it moves, and then match the tracks. We can match each one of those tracks to the tropical cyclone tracks, and again, understand whether or not these things end up being seeds. We're doing this through these hundreds of years of simulation, and we want to understand what the impact is of the various decisions. And one of the clear impacts on these is whether or not we use convective parameterization. So in this case, I show what the track density is in observations, and in Hadjam, we tend to have a bit too many at 10 kilometers, and the size is wrong. And then in the end, you attribute precipitation to these. You end up with the right precipitation for entirely the wrong reasons. On the other hand, if you disable the deep convective parameterization, you end up with just about the right number. And particularly, there is a huge error over the Amazon that entirely goes away. But this decimates the tropical cycles. So you at 10 kilometers again, the scale is not the best scale to make these decisions. It would be much better to be operating like Bjorn and the others in this so 2 to 3 kilometer range. That's great. But yes, sure enough, if we are a bit out of time. Yeah, that's fine. Just to say, one of the things that we found with the full spectrum, we have a strong error still in the diurnal cycle, and if we disable the deep convective parameterization, the diurnal cycle is strongly improved. Okay, I talked about TC frequency, which we've been able to match. I found that the full range of intensity reached about 10 kilometers, and I've been looking at these seeds and understanding what constitutes a seed and what doesn't constitute a seed. I've yet to look at whether or not in the same way as I did look at them in a statistical way in my paper, but not really great. So that's the next thing I'm going to do. And I'll stop here.
Thank you very much, Pier-Luigi. Very interesting talk. Seems that we still need an ensemble instead of just one simulation of 1 kilometer and just one single run that someone is advertising in Europe for a while. So thanks.
No, nobody's saying that. Nobody's saying that.
So perhaps we should also have some discussion about this on how to make a statement that we need a variety of models, sample simulations, parameterization, and different community working in just one magic solution to save the world.
Nobody's saying that. People repeat that, but nobody's saying that. I know who you're talking about, but nobody. Yeah. Yes. Good.
Okay.
Good.
Great.
Okay, so I have 2 questions. First one, you said, oh, you get your Cat 5s with 10 kilometers. You probably know Chris Davis' paper.
Yes. Absolutely.
And I thought he said that paper you need about 4 kilometers or so to get your Cat 5. So that's my first. So I wanted to comment on that because 10 kilometers to 4 kilometers is a big difference.
Yeah.
The second wasn't clear what I have looked, because I have looked a lot of this stochastic parameterization, the CMWF system, and you have a billion more tropical cyclones running this stochastic parameterization. But I didn't get what happens with the disturbances in the stochastic parameterization. You went a little fast. So that's my 2 questions. Thank you.
So the first thing, remember I said from that slide onwards, I was just showing atmosphere only, not coupled. So of course you're going to overestimate intensities and all that. If you look at the coupled, the curve shifts. And then we've been messing with this forever. I'm showing you the curves as Malcolm produced them, which are in all the papers historically, okay? This conversion of 1 to 10 minutes and all that, to make all the basins homogeneous, this is really delicate. Okay? Depending on what you do, the curve will shift, okay? And you may end up saying, I'm no longer in the category 5 territory, okay? But the shift between 60, so it's 100, 60, and 25, and 210 still is a very big one. It's a very big jump, yeah? So we'll see in Erie. In Erie, I'll have, again, a very big sample of coupled simulations of 10 kilometers. We'll see in Erie whether this is reproduced, yeah? But remember, these are atmosphere-only results, yeah? Let me show you the stochastic for a second. So I said, the stochastic parameterization in the Met-Office model behaves quite differently from the stochastic parameterization in the IFS. And this I discussed in my paper. The 2 things, although some of the schemes have the same name, the two things are quite different, okay? But just to say what happens in our model, so you see, this one is the 60-kilometer model, this one is the 25, and these are 3 of the 10-kilometer model. You see that as we come down, it's this blue category that suffers the most, and this I also show in my paper. So this natural selection affects mostly this first bit. It does affect everything, but the ones that suffer the most are the very weak category. Yeah. In the IFS, it's different. In the IFS, you come up to the right resolution, and stochastic physics behaves very, very differently, despite some of the schemes having the same name. It's also because people have beliefs in which part of the stochastic physics forest is more important, and so they put different weights on that. So when you say I have stochastic physics on, it's a family of schemes, and each has a different weight and has a different implementation. Yeah. So quite a messy. That's why it took me 3 years to do that paper. It's quite a messy field. Yeah.
Thanks. I think we close here and we go to the break, and then we can ask still the questions, because otherwise it will be late for lunch, and you see that it's complicated to go to the canteen. So we go to the coffee break, and we have the cathedral to continue the discussion. Thank you very much.
Okay.
Yeah, we go to grab a coffee and we keep discussing, and then we come back at 11:30 for
discussing the cathedral, right?
Yeah, for the second part, the part of the discussion of the construction.
But you can do that in the cathedral.
Yeah.
Right?
Okay, so we will go to the cathedral and just stay in the cathedral for the rest of the morning. Yeah, sure.
We can connect on the Yes, yeah, I will do that. Program back or snack, or that you might have. Okay, I will show you.
the method is kind of newer and newer things. And you can look, I want to know conversion. Don't change the model defining. Don't look at that. What you want to do is try to build it all the time. This objective every year is to reduce the underlying. So we keep dropping down, but again, it's not knowing where the hell we are. We're generating, we're generating fusion because people are not models say, but you said, I don't know. No. Okay, look, we try to agree. We're talking about progress. However, we try to do that. We can't agree. Somebody goes off, either fire, and that's something else. Fire eventually teaches it to me, right? So beyond now actually understanding it, coming back to say we need a protocol and that's everything. I find it so fun to read this because for you, it's that. It's all about spontaneity, but then it's confusing, right? So anyway, unfortunately, 10 kilometers is no good. And a lot of people are choosing to like to that. So going sub 10 kilometers, as a mind. The multi-decadal runs dump is large enough. Be very optimistic. So I guess, taking a practice, choosing, some version of that is computational track and tuning it again, reasonable today's methodology. Well, I think it's defensible if you're trying to use it to make some decisions. There are different approaches to trying to understand it. So Pankov, that's a great problem, has been shooting the part of the trial. You can use the full speed device of the young people born with a different part. However, then it screws up the repeated bias. This is where science